Log on, tune in, find out. Another good idea from Cambridge.
Morning session on this last day, and the first speaker, very well known to our audience, is Alexander Itz from Indiana University, who will talk about discrete Painlevé equations and orthogonal polynomials.
Thank you very, very much to organizers for inviting me and giving this opportunity to talk here. So I'm going to talk about orthogonal polynomials and Painlevé equations, both continuous and discrete. I shall start with setting the Riemann-Gilbert formulation for orthogonal my main goal, my ultimate goal, is to present some results concerning the global asymptotic analysis of some solution of some discrete Painlevé equations which arise in the theory of orthogonal polynomials. This is so I shall start with setting Riemann-Gilbert formalism for orthogonal polynomials, with which help these results we obtained. Also, this would give me the opportunity to introduce the discrete Painlevé equations, at least half of them, in a very natural way. So there will be not much new in what I'm going to talk in this part of the talk, and except perhaps maybe some distribution of accents on the issues. So this is my main character, of course, the system of orthogonal polynomials. On the line, the polynomials are monic, and they are orthogonal with respect to a weight. I will assume that weight is exponential, which is not actually too necessary for many algebraic aspects of what I'm going to talk about. And I will write the weight in this form. So this is the polynomial exponent Tg Zg to n and T to m greater than 0. So this is perfectly okay if everything is real, they exist. So this is my object. So what are the principal object of interest? So I just want to overview to set the environment. What is the principal object of interest? Of course, it is the polynomials themselves, and plus this is Hn, their norms, and recurrence coefficients, of course. They appears from the fundamental three-term relation. So this is, of course, absolutely fundamental things of the theory. So they are principal objects of interest. And what is the principal analytical question? It is the asymptotic behavior of everything when n and n. This is why I kind of factor it out, the n. So this is the n goes to infinity, and the sort of parameters might belongs to some approach certain T naught. So this is sort of zoo. There is a zoo of asymptotic behavior, of course. So it depends. It comes a lot of everything which comes from the application actually comes with the physical meaning of those T's. And so in the physical meaning of this T naught, so usually there is a open sets of parameters T when you have the more or less simple structures of asymptotics, and then there are transition limits. This is the way, by the way, Painlevé equations appears in non-trivial way in the theory. So now a few words about connections. So this is, of course, very classical domain, and it has profound connections with other classical branches of classical analysis. So most fundamental are, of course, with the special functions, with the Toeplitz and Hankel determinants, with Jacobi matrices. So this is a spectral theory of Jacobi matrices, of course. And Well, more recently, random matrices. And perhaps the most recent, it is the connections to integrable systems. Actually, the connections to integrable system is not very recent. In fact, it is through Toeplitz and Hankel determinants. Of course, orthogonal polynomials appeared in the exactly solvable models of statistical mechanics for decades. In soliton theory, it appeared at the very moment in the early 70s when the Toda lattice equation joined the list of fundamental integrable equations. But what happened in the last couple of decades, it is quite remarkable. So this relation between orthogonal polynomials and integrable systems began to be really appreciated and used by the orthogonal polynomial community in large. And actually, that is quite remarkable. And several long-standing problems were solved, and several new avenues of research were discovered. And one of them, of course, the relation to discrete Painlevé equations. So I am going to now to describe the relation to discrete Painlevé. Actually, orthogonal polynomials formed historically one of the three general contexts when the discrete Painlevé equation appeared first time in 1990. So the other two is the theory of integrable mappings of Niehoff and Papageorgi, and the third one was the discrete Lie symmetries, which started developed at that time by Winternitz and Levin. Now, relation so in my descriptions of relation to orthogonal polynomials, I will to discrete Painlevé equation, I will use Riemann-Hilbert formalism. So again, this is a framework when they appeared, when this relation appeared among one of the first times. And moreover, this formalism allowed to address and to solve this principal analytical problem. So this is why there is importance in this formalism. Okay, let me now remind. So usually what I'm saying, it is already 20 years old, but still let me put it in my talk. So how we come, so how we relate Riemann-Hilbert problem to the system of orthogonal polynomials? We just defined a 2x2 matrix, which is the first column is this. Then it is the second. So the first column is just orthogonal polynomials themselves. And the second column, it is the Cauchy transform of the first column. Cauchy transform with this weight. So this is the matrix. So let's consider this 2x2 matrix. Minus h and minus 1. So I just did a Fourier transform of the first column. Okay. So what are the properties of this matrix? So there are three characteristic properties. So first of all, of course, it is analytic outside of real line, which is absolutely trivial. So the first column is polynomial, the second is a Cauchy. Then, because of the second column is a Cauchy transform, we have a jump. There is a jump which is a triangular, which is exactly given by this formula. So on the real line, we have this jump. And because polynomials are orthogonal polynomials, we have a specific asymptotic condition at infinity. So sigma 3 is of course 1, 0, minus 1. Okay, so so this is very simple. So this is very simple. This is straightforward. What are the two? Yeah, sure. Thank you. Yes. So this is so what is important? Although again everything is simple but fundamental. Important is that we can make two observations. The first observation is that these three conditions defined y uniquely. So very easy to check. The second observation is that this is the particular case of so-called Riemann-Hilbert problem. So Riemann-Hilbert problem, it is a problem of finding function if you know its jump on a contour, maybe on system of contours. And it is normalized at infinity, say, as 1. So this particular case. So we have see the contours, it is real line and say big circle, no, maybe not necessarily big, unit circle. And this is a jump matrices. This is jump matrices. So this is so from the first observation. So now what are the conclusion? From the first observation, it means that we can forget about this formula and to study orthogonal polynomials just to study this problem. So because it is uniquely determined. And if we study this problem, we can recover everything about orthogonal polynomials. This is my important data, as of course Pn is just y of z. Hn, I believe it's going to be minus 2 pi I m1, 1, 2. So this is, if I write I of z as a full series which exists. So this gives me h1.
In the asymptotic behavior at infinity, you're using, did you say orthogonality, but are you also using the fact that the weight is the potential is a polynomial?
No, I basically use that there are all moments, of course. So it is enough to have all moments. Yeah. Okay. Yes, so this is the same thing for the demands because all this is very algebraic, very formal, which can be always made. So for this weight, everything can be made immediately explicit and exact because this is a very good weight. All my boundary values are attained in the uniform sense. The asymptotic is in the uniform sense, so everything is without any question. More interesting when the weight becomes more less good, then you have always every time to explain exactly what all this means. In this case, there is no need, so it is everything is very simple. So this is so from the first observation, it means that I'm just have to solve independently of this formula, this Riemann-Hilbert problem, and then I can reconstruct all the object. So Rn comes from Hn, of course, it is Hn over Hn minus 1. Qn, it is the difference between the, okay, so they all are reconstructed from the M1. So this is the ideology. So this is the first conclusion. The second conclusion, the conclusion from the second observation is that it means that to study orthogonal polynomials, we can now apply the apparatus of classical apparatus of the theory of analytical of boundary values of analytical function plus the modern Riemann-Hilbert technique which have been developed in soliton theory starting from the pioneering work of Zakharov, Monakov, Shabat and culminating in the David-Joe nonlinear series descent method. I hope I will have some time to say more about these techniques, but I don't think I will. And but now let me to finish with this. But now let me indeed do the, in a sense, simpler things, but still fundamental. Now let me use this problem to introduce discrete Painlevé equations. So now I can indeed, where is the eraser?
It's under the rectangle.
I still don't. Yeah. There are too many. Okay, in a sense, I can erase this. Oh, you can, in fact, I can erase it. So this is the point. I don't need this formula anymore. Yeah, I can erase it. Yeah, that was important. That was a psychological moment to erase this formula. Because you always think, okay, so what? This is really, yes, this is, but it is explicitly solvable. But the point is that you have forget about it. Yes, and try to do it as though it is, try to work with it as though it is not explicitly solvable. Okay, so now what do? So what are discrete, what are equations? Equations are some kind of dynamical system, some kind of differential or difference relation on the objects. And for this kind of type of Riemann-Gillier problem, of course, there is you can write a very fundamental set of linear differential equations. So you only need to, now I use this formula. I use this way. Let me introduce just this, let me kind of incorporate this exponent into y, so that for psi function, I would
Is there a V
have,
missing?
huh?
Is that an N or a V or
Sorry?
Sigma.
any exponent?
Sigma 3.
Yes, thank you. I have to be, okay, V of z over 2 sigma 3. Yes. Sigma 3 was, sigma 3 is sigma 3. Yes. So now we have, so what we have for psi? We have that psi plus equals psi minus. And the matrix is constant, so I just eliminate. But the price is that, of course, now I have asymptotic behavior, more complicated. It is my previous asymptotic series. Now it is, I have to introduce this essential singularity and still have, let me write it in this way, kind of the formal monodromy, as a way of formal monodromy. So now this is, the problem becomes as a monodromic problem, of course. And we immediately conclude from the, again, from the people, especially from soliton theory, it is straightforward. It is at once. There is no discussion what to do next. It is to consider 3 logarithmic derivatives. Let's call it A of z and d psi dtg psi minus 1, tg is this time. Let's call it vg of z. And we have discrete variable n. So it is cn plus 1. When I, so here n is everywhere the same. So I should introduce n, of course, in everything. But here it is important because I'm going to do discrete logarithmic derivatives. It is u of z. Now, because this is a constant matrix, all these derivatives, all these functions are entire functions. There is no jumps for them. And the only singularity in our case, they have at infinity. So they are polynomials, in fact, at infinity. A of z is just, you know, what is the power? Yes, it is some ak times z k from 0 to 2m minus 1. So this is a polynomial of this power. Actually, a 2m minus 1 is immediate. It is minus n minus 2m n sigma 3 t 2m sigma 3. So this is there is no 2 because I divided by 2. Okay, if I differentiate 2m. Yes. And of course Vg is going to be a polynomial. Vg is a polynomial of degree, of course, Vgk, zk, k from 0 to j. And all those coefficients can be expressed in terms of those m's. And so it means that in terms of rn's. So in terms of the recurrence coefficients. I'm not going to give it those, although it is possible to write these expressions for the general case, using, for instance, the Jacobi matrix, and in fact, they all can be written in terms of this matrix. So you take V prime, and L is a Jacobi matrix constructed, and from this derivative, from this matrix, you can write all the coefficients. There is one, of course, this one, it is fundamental. It is always the same for everything. And it is U of z, it is z minus qn. And here it is something like hn over 2 pi I over hn, if I'm not mistaken. Let me just double check quickly. Yes. Yes. Yeah, with a minus, almost correct, with a minus. Okay. So I want also to emphasize. So it means that the solution. So what is the conclusion? It means that the solution of my Riemann. Okay, I probably. Yes. That it means that the solution of my Riemann-Hilbert problem, that psi satisfies. I can now look at this from the other side. Satisfies the system of three type equations. This one, dpsi dtg, and psi n plus 1 u psi n. Okay. Important thing to remember that. Important thing to notice that to do all this, it is not necessary to have this in the simplest way. So basically, you can do all this to what is definitely would be enough to have this as a rational. Then those guys are going to be just rational functions, which are also computable. And this has been done a lot on this generalization to the rational functions by Magnus, by I believe Walter probably will tell about this more. So there is a very interesting and very important, the kind of the line of research which have been streamed from 90s and about this semi-classical orthogonal polynomials. So you always can write this thing, and this is again because you always can get it from your Riemann-Hilbert problem, throw away these things and write it, and you will get it immediately. Important, I also want to make important point that I don't use to write all this. You don't need to use any orthogonality condition. You just use Liouville theorem, and it means that this system is written for much more general Riemann-Hilbert problem than we started with. You don't need to just jump on the real line. For instance, for this one, the real line with this matrix. All of this would be written in the case of my polynomials on the more general problem is this set on the system of 4m, 8m rays with the triangularity matrices, flipping. So this is a full isomonodromy problem for this. All this is this. And so my orthogonal polynomials is just the particular solutions corresponding to the fact that all half of the Stokes matrices are trivial. So that is the kind of the general remark. Now let's back to the system. Now where is the discrete Painlevé equation comes from? Of course, from this compatibility condition. So when I consider this compatibility condition, what I get the following relation: U of z equals an plus 1 u of z, u minus u an. So this is the kind of the compatibility condition of those two equations. It can be again written, in fact, it can be written as a nonlinear difference equation for the recurrence coefficient. In my particular case, it can be written, in fact, as this, and v prime of L and n minus 1 equals n over n, and v prime of L and n equals 0. So this system It actually can be written as a v prime of L plus commutator with L equals 1. So this can be written in all this. There is a lot of interesting combinatoric behind, of course, this formula. So in particular case, now, so this is a general high order nonlinear difference equation, which are integrable by construction. So they are just, this is a Lux pair for them. This is Lux pair for them, and that was the Riemann-Gilbert problem for them. This is all you need to start solving this system. And again, this can be written, this can be done, not necessarily for these simple weights. So important things that you can actually extend it to any semi-classical weights, of course. And even more, you can even extend it to the, even this is not necessary. And I will show in one example, even this is not necessary. You even can write some sort of the general relation for almost arbitrary weight, which was done in the work of Chen and Ismail. So there is a lot of, and I am not an expert in the non-trivial algebra, which actually developed since 1990 around this, and led to the very, very non-trivial algebraic constructions, which are not of course the subject of my talk, and I really don't know it. And but when you take, so where are discrete Painlevé equations? When you take the first non-trivial v, then you get the first non-trivial v, and I will show it right now in my examples. The first non-trivial v would lead to the second order difference, to the second order difference relations. And they are, if you like, by definition, discrete Painlevé equations. They are, first of all, well, and more seriously, they are integrable because there is Lux pair for them. They describe as discrete isomonodromy deformation of this system, the Schlesinger deformation, in fact. So this is kind of another. And they, mostly of them, satisfy the confinement property. Again, kind of just like if you consider continuous isomonodromy deformation, they necessarily satisfy Painlevé property. This is the theorem of Miva and Malgrange. Similar exists for this, but not okay. In the discrete world, not everything that easy. So it satisfies the classification of Niehoff Romani grammaticus of the characteristic property of discrete Painlevé equation. But strictly speaking, this is a half. So this is a D Painlevé, not Q. So this is so to get Q, you have to replace this equation by the discrete as well, and relate everything to the discrete orthogonal polynomials. Very good. So this is, I believe, the end of my first part. And now I really want to overwhelm you with the formulas, so I'm going to this. And only very last remark. Of course, we can commute everything, the other equations. So when you commute this and that, then you get, of course, isomonodromy, continuous isomonodromy deformation, continuous Painlevé. So you always have, immediately from the very beginning, before any limits, you have, of course, continuous Painlevé in your orthogonal polynomials, with the simple weights. When you commute this and that, then you get the total lattice systems types. When you commute those guys for different J, you get the KDV types of the very. So this is all in it, and this is all which basically, without orthogonal polynomial context, what was present in this seminal works of Kyoto School. Okay, now let me consider examples, and let me indeed show that to go to analysis. So I am to show that to present some results which were obtained using this ideology, using this formalism, and kind of to show you what kind of the result. But first, I will consider the trivial example, just to again. So let's start with so this is a trivial, of course, example. So when I have the simple, when I just have my Gaussian weight, V of z is z squared, then there is no Qn. There is no Qn because it is even. Then it is very easy calculation, just in one line. you plug into this equation the asymptotic expansion, the first asymptotic expansion, plug it in, and you calculate that A, of course, must be linear function because you differentiate the square of V, and you get this linear function. So this is the expression of the zero order term. Freud equation. Well, of course, if I had to say that an orthogonal polynomial, this is of course Freud equation. This is of course nonlinear. So again, equation on nonlinear coefficients, nonlinear difference equation of recurrence coefficient were written for many years already. Been written many years. But I believe, and they were written also. So in orthogonal polynomial community, this is usually called Freud equation. In theoretical physics community, it is a discrete string equation. Yes, and so they were written for the probably since 30s. Yes, but I believe, and they also were understood as a compatibility condition too. But I believe it was we who first used the fact, the kind of realize that they're integrable. So they're integrable, that they can be, that this fact can be used to solve them. Okay, so anyway, Freud equation is of course becomes trivial, becomes just linear and solvable. So this is you have the explicit formula for Rn. And of course this is the Hermite polynomial. So if you write your linear equation for the as a second order differential equation, you get parabolic cylinder equation. So your polynomials are Hermite polynomials. So that's the end of the story. So this is the first non-trivial. This is the first trivial example, but it is trivial in this context. But of course, Hermite polynomials are not a trivial thing. So that is a very important thing. Now the really first non-trivial example. Really first non-trivial example. So we are going to the again. I want to keep evenness. So there is no Qn. And so I can see the quadric. So tick boy, again, Qn is 0. Now you have to wait maybe about 15-20 minutes to write these formulas for A. So this is polynomials of the cube. It is a third order polynomial, and it involves again Rn. Rn involves the recurrence coefficient. Again, it is straightforward. It is just you substitute this expansion into this equation. You equate the powers of z. A priori, you know that it must be polynomial of the third degree, and you are done. After that, of course, you write Freud equation. It becomes very well known, of course, in this audience, equation, which I believe it was in our paper with Thanasis and Zhou, first coined as a discrete Painlevé one in 1999 paper. At least we wrote it. So we will call this equation discrete Painlevé one. Although, of course, it appeared in the Brizan and Saxon Zuber. It is in the theoretical physics community. You know, Schohat. Okay, probably this is the first one in 1939. But and of course it made a splash in 1990 in the famous works of Brizan Saxon, of Brizan Kazakov, of Migdal Gross, of Schenker, of Douglas Schenker. But even they did not call it discrete Painlevé equation because it was not realized that this is integrable itself, that continuous limit goes to Painlevé one. But its own integrability wasn't quite understood. Anyways, this is about the non-trivial results concerning the global asymptotic analysis of this equation. So I consider the case when A equals 1 and t less than 0. I have to consider this. So I have actually to rotate. So anyway, this is a formal. So first I present some formal statement. So if you consider this double scaling limit around this point, so which turns out to be a critical point, if your ratio strictly above or strictly less, then the asymptotics is given by the asymptotics of recurrence coefficients is given by elementary functions. Now, if you are in the critical and the different types of well, this is the transition. So if it is critical point, you have to consider if you just plug this ansatz into Freud equation, you arrive with the proper choice of the constants, which is not, of course, that important, to this equation for u which you took in your answer. This is the Painlevé 1 equation. Moreover, you would actually moreover, so this is of course limits absolutely formal. You just plug it into equation, but you started with your orthogonal polynomials. So you want to see. So you had very particular solution of your Freud equation. You want to see what it is. And so, it was established by these people that it is equation. It behaves like this square root at minus infinity. Unfortunately, there is one parameter family of Painlevé 1 solutions that behaves like this. So there was a question of characterization. Well, first of all, rigorously prove and characterize this solution of Painlevé 1. And this is the answer. So first of all, of course, to accommodate this limit, we have to take t negative. And so it means we have to somehow to analytically continue my orthogonal. So replace. Consider not the orthogonal polynomials on the line, but you can consider the general situation on this combination of the rays. And then the answer is the following. Indeed, if I start with if I consider the solution of my Freud equation with the initial data which are given by the R0, R1, which came from the orthogonal polynomials, at large n limit, which I described, it would behave like this, where this coefficient of x is a scaling parameter, indeed, belongs to this Tranché solution family. So it indeed belongs to this Tranché solution family. So this is a solution family which actually has this asymptotics on this sector. Still the question, what is how we can characterize it? So in fact, you first have to decide how you can characterize solution from Tranché family. It also, what is of course there is this approach, there is this view that it is the difference on the solution is on the beyond all orders, on the exponential correction. But you have to introduce the rigorous notion for this exponential correction. So how it can be done? It can be done by different ways, but one of the ways is the following. There is, among all these three Tranché families, there is exactly one solution which is determined by this asymptotic uniquely. This is solution which actually has this asymptotics in the larger sector. There is one, it is called Tranché solution. All of this was known by Boutreau, of course. And also generally, so it behaves in this large sector like this series. There is exactly one. So in this family, there is exactly one. And now you can, of course, compare any other solution from this family, as a difference with this particular one, which is uniquely defined by this asymptotics. Now the statement, when alpha is 1 in this combination of integrals, then it is exactly u1. Then this u alpha is exactly this Tranché solution. If alpha is not 1, then it is u1 plus this exponentially small correction, and a alpha is given by this formula, by this explicit formula. So it was first derived, and so again in 1990 we wrote in the short period of 1990-1991. We with Thanasis, Zhou, and Kitaev, Sasha, we wrote a series of papers when we first put everything in an isomonodromy context, just to calculate this thing in isomonodromy context. And first who calculated it was Sasha Kitaev using this isomonodromy context. Then we put it in the Riemann-Hilbert context and kind of redone it for more general case. Still, in all these works, we had at this time our ambition was to show physicists that we not only can rigorously prove something, but we can derive formulas. So that was we had gaps. So in all these papers, there were gaps of the mathematical rigor, which were completely filled by the youths and Quigellers very recently using already the Dave Joel approach. Yes.
So, excuse me, I just missed something. U alpha is the generic Tranché solution, is it?
Yeah.
So what you say that every Tranché solution is a 3 Tranché plus a correction term.
Yeah.
Does this mean that also the Tranché solutions are pole-free in a big sector?
Huh?
Does this mean that also the Tranché solutions are pole free in the big sector.
No, why does it mean? On the boundaries of the sector, this correction, this exponent becomes oscillatory.
Oh, okay.
Yeah, so no, this is the whole point. This is a quasi, this is a Stokes phenomenon. This is a quasi-linear Stokes phenomenon. That's the whole point. If alpha is 1, there is no this, and then you kind of can continue beyond the boundaries. No, this is very interesting, you know. So this is a separate question about the use of Riemann-Hilbert approach to study quasi-linear Stokes phenomenon. This is actually was one of the first example of this thing. So this is an example of this is a very old. Again, this is 1991. There is a second continuous limit of this equation. It is this. So now it is just the normal thing. T is greater than 0, A is negative, and now this is the critical point. And now all the scales are different. So if you plug in this, if you assume that your n over n is around this particular point, x is a scaling parameter in all these scales, and you plug in this sort of ansatz, then your u now satisfies the second Painlevé equation. And again, solution which should be chosen. Now it is you need to do nothing. You just start with your real line. It is the Hastings-MacLeod. It is, and it defined by this asymptotics uniquely. So that is it. And this is also was again on the formal level noticed by physicists, and we with Pavel Blecher proved it rigorously during all these years. It is interesting. I think that if this limit appeared first in the physics literature, we probably would call this equation Discrete Painlevé 2 equation. Anyway, there is of course continuous. With the continuous Painlevé, everything is very easy. You just have now I am not going to do any large n limit, so I put my n equals 1. T is 1, A is x. Now A is so just I remind you that my V of Z is A over 2 Z squared plus T over 4 Z4. So A and Z is T, it is this times Tj. It is this Tj. So I just choose n T equals 1. Of course, there is only one parameter here. You by scaling could make this T1, and I choose on 1, and so A is 2x. So x is going to be dynamical parameter. And you can now just introduce, and you can now just rename this my pair which I have before. So this is just derivative with respect to A. It is a second order polynomial on Z, and this is my derivative which is a third order polynomial of Z. I just rename. I introduce the letters, and then I look at the Jim Bemivo and the list, and of course I recognize immediately that this is Lux power for Painlevé 4. And so this is a statement with all this specification. Rn, it is a function of x, and it satisfies Painlevé 4 equation. That was first noticed by Kitaev. Also, okay, during all this, our worked in all this business. So this is, but again, you see this Painlevé equation, much more kind of the context which we have this Painlevé equation, much different comparing with the previous one. In the previous one, that was a genuine transcendent. It was not elementary. This is an elementary solution. So what we are talking about, this is Rn. It is a certain Hankel determinants which satisfies this equation. So this is a statement. This is a rather not the statement of that something is described by Painlevé, but the statement that actually this my Rn provides a special solution for Painlevé 6. So that is the sort of the answer. Well, that was the old examples. Now the very recent example. So, but again, I am playing around Gaussian weight. Now I just distort this Gaussian weight by jump. So I take so this is my Gaussian weight, and I times this to the jump is written in this way, in this form. Yes, It is, there are reasons. You can actually reduce any jump at one point, constant jump to this one. But it goes back, I will talk about it, goes back to the famous Fisher-Hartwig singularities into opposite determinant. So we have this. So we have a point and we have a jump, which is described by, and beta is arbitrary complex now. Now, of course, I have in addition, okay, I write immediately Riemann-Gilbert problem for psi function. Now, of course, I have my jump, but in addition to jump, this is the usual jump for psi, but in addition to this jump, I have to describe the behavior of my function near point m mu naught. Because now it does not exist there, it is a singularity. And this is a regular singularity. It can be easy check that this is this logarithmic singularity. This is a nilpotent matrix times the constant matrices which are different in different quadrants near the point mu naught. So this is a description of the Riemann-Gilbert problem. There is no big difference in consideration the logarithmic derivatives. And now I come up with a system. Now my triple is this. So of course this comes, you see, this is what I would have had if it was just a Gaussian. It was what it was in the Gaussian case. And this is a contribution from the jump discontinuity in the weight. The regular singularity of logarithmic type. So now it is non-trivial, of course, equation. And then I have, of course, derivative with respect of jump. Now the parameter is jump. And this is, of course, standard recurrence three-term relation. Now the Freud equation in this case, of course, becomes a map from this Qn Rn. Now I have Qn, it is not anymore even potential. So it is a map from Qn Rn to Qn plus 1 Rn plus 1.
We couldn't see.
Okay, yeah. So it is a map from it is nothing, I said, I just said. Now it is equation. Now it is equation. Okay. I don't know what is this. So I ask Grammaticus in his list. So I cannot find it immediately. So I don't know. It is not quasi-classical weight, by the way, because it is not rational function. It is with delta function. I don't know. So this is, but again, but it is integrable. It is second order difference in linear equation, which is integrable. I have Lux pair, I have Riemann-Gilbert problem. I can do the whole asymptotic analysis. And I'm going now to present the results about asymptotic analysis of this thing, of the solution of this thing. And but before, just smaller. So what is the continuous Painlevé equation in this case? It is again Painlevé form. So it is again Painlevé form. It turns out that continuous Painlevé equation is again Painlevé form, with respect to the position of the discontinuity. Now, what is the continuous limit here? So why? So I provisionally call this system Painlevé 34, discrete Painlevé 34. Why? Because it has limit, of course, continues to Painlevé 34. So the critical point is this. First of all, since I don't have capital N in front, I have to rescale everything. So now, to get non-trivial result, I have to assume that mu naught behaves as square root of n. So this is the right scaling. And it is, if it is greater than square root of n, then it is there is elementary asymptotic. If it is less than square root of n, there is also elementary asymptotics. In the around square root of n, you have to introduce this scaling. So this is where you have non-trivial scaling limit. Then it turns out that you have to introduce the scaling in this way. This is 2/3. Then your Qn Rn behaves, okay, this is ansatz. And then when you plug it into those my discrete Painlevé equations, you obtain for V this equation, which is the particular case in Painlevé 34. The general Painlevé 34, you have to add plus alpha squared. So there is a parameter. If alpha is 0, actually it is, well, it is what it gets, but it is very easily reduces to Painlevé 2. So if V equals U, you just make the substitution V equals 2 squared, and you get Painlevé 2. And what is the solution? Interesting enough, the solution is Ablovis-Sigur family. To me, it is the first time Ablovis-Sigur family, not Hastings-MacLeod, but the Ablovis-Sigur family showed up in random matrices in a sense. So it is described on the plus infinity as again as this exponent, just like Hastings-MacLeod, but rho is not 1, is less than 1. It is given by this formula when gamma is my beta. Okay, I took to be absolutely correct. I am taking beta to be pure imaginary, so it means that my jump is pure real. So the most interesting case, right? Pure imaginary. And this imaginary positive gamma, so I express this exactly in terms of gamma. And then the Ablovitz-Sigur connection formulas gives me, of course, behavior at minus infinity. Behavior at minus infinity. So this is just to give you a flavor of the things what we are doing with the asymptotic analysis of these discrete Painlevé equations. I would just present the results what is going on when mu naught is strictly less than square root of n. So if mu naught is strictly less than, so if mu naught is square root of n and lambda is strictly inside minus 1, 1, then the asymptotic for Qn and Rn is given by elementary functions. It is not banal, but it is elementary function. It is oscillatory asymptotics whose parameters are given exactly. Gamma is my parameter, is my original parameters, whose amplitude parameters are given in terms of the absolutely elementary functions, amplitude parameters, the frequencies, and there are phases. Theta 1 and theta 2. Those phases are calculated already. They are not that trivial. They are given in the formulas in this form. The formulas for these phases includes the gamma function. This is a very familiar formulas for the people who's been involved in asymptotic analysis of integrable PDEs. So this is a sort of this kind of, but and actually this asymptotic behavior can be seen to be match my Painlevé Ablovitz-Sigur formula when I approach the edge from inside. When I go to outside, it becomes exponentially small, and all the limits becomes just Hermite limits. N over 2 and Q goes to 0. And this was independently established by Johansson, in fact, so that behavior for these outsiders. Hankel determinant. So this is a tau function. So in this language, the recurrence coefficients are, the orthogonal polynomials are intimately related to Hankel determinants, which are of their own interest. So for Hankel determinants, we get the asymptotics of the. So this is in the language of discrete Painlevé equation just a tau function corresponding to this solution, and this is a formula. So it says that with large n, if I consider the ratio of my Hankel determinant and the Gaussian, just the Gaussian, which is given explicitly, it is given by what is important. It behaves. It has as a function of n. It has a power-like behavior with this dependence on the beta. Then it has some. It is not necessarily oscillatory because usually beta is pure imaginary. So this is a sort of Sigur type asymptotic behavior. So now I begin to use slightly using the terminology from the theory of Hankel interpolus determinant. So this is a kind of Sigur types asymptotic. This is a Fischer-Hartwig types of asymptotics. This is what the power-like behavior, and this is a constant. This is a dependence on lambda and beta. It actually involves this beautiful special function, Barnes function. So this is one of the first, actually I believe, first result of the asymptotic evaluation of Hankel determinant with the Fischer-Hartwig type singularity. So there's been many results, beautiful results concerning Topliss determinants, but for the traditional methods, the Hankel determinants, they pose problems. And with Riemann-Hilbert approach, we were able to overcome those problems. And the last things which I would overwhelm you, it is the general formula for the Hankel determinant with a symbol on the interval with the most general Fischer-Hartwig singularity. So it has it has the smooth part, which I would call secure part. Just e to the ux is a very good function. And then it has the root type singularity at point lambda j. I have points. And at each of point, it has again jump. So this is a Hankel analog of the Fisher-Hartwig weight. It is not already any more Painlevé equation. It is, of course, the isomonodromy deformation with the r plus 1 regular singularities. So it is not anymore. It is kind of generalization. And now let me present the result of the asymptotics. So to present the results of the asymptotic, well, I will torture you a little bit. So you have to introduce some objects. So this is just the flavor of the result. You have to introduce some, this is the sum of all alpha. Then you introduce the weight on the circle. You kind of can map the interval to the circle, and then introduce this function v on the circle. It's going to be even function on the circle by this formula from my u to v. It is also important, and my point lambda g, they go to the point z's on the unit circle. Now you do what is very, very typical for the analysis of Toeplitz determinant. You do you consider the Wiener-Hopf factorization of this symbol on the plus function, minus function, and just the average. And in these terms, the asymptotics is given by this formula. So the ratio again of my Hankel determinant to the Hankel determinant of Legendre polynomials corresponding to Legendre case is given by, so this is a Séguier type. This is the asymptotics of this is exponential asymptotic with the linear exponent. This is a Séguier type asymptotics. It depends on the average it depends on the Séguier type weight, and in a very simple way of my Fisher-Hartwig. So this is the addition which comes from the Fisher-Hartwig singularities. Then there is this power-like behavior. This is what typical for the Fisher-Hartwig on the Toeplitz case. Again, it is very similar for the Toeplitz on the, and this is addition from that. This constant e. So important thing always is constant e to trace. And this constant e is quite a constant. Here it is. So this is a dependence on constants e of the Séguier part. So this is a dependence on the Séguier part. So this is again, the expert could recognize in this part and in this part the Séguier part from Fisher-Hartwig formula for Toeplitz determinant. Then it is a dependence, elementary dependence on the parameters of the Fisher-Hartwig singularities. This is elementary part of dependence. Alpha, beta, lambda, lambda. And there is now non-elementary part of dependence on alpha and beta, which also involves Barnes G function. In fact, in application, it is indeed important to have this constant. It is not just the kind of analytical quest for the perfection. It is in fact because all these parameters in the statistical mechanical applications, they are physical parameters, and you really need them to know. Okay, so this was done in a very this is the result, a very recent result of our with Percy and Igor, where we also proved actually the long-standing Bazor-Tracy conjecture for Toeplitz determinant. I don't have time to describe it. My last remark is that because of these results for Hankel determinant, we actually can do what also was a sort of the long-standing problem, the asymptotics of so-called Toeplitz plus Hankel determinants. So it is again an application in statistical mechanics, in number theory applications. So when you consider random matrices not over GOE but over symplectic and orthogonal ensembles, you actually come up with the necessity to calculate determinants. So you have one weight on the unit circle, and you calculate its Fourier coefficients, and then you construct these 4 types of matrices, kind of Toeplitz plus Hankel with the different shifts they appeared. And the problem was to calculate the asymptotics. But it has been for some time. So we took it from the papers of Bayek and Reines, where they did it the most, all these formulas. So you see, these formulas represent all those Hankel plus surplus determinant in terms of just Hankel determinant with this Fisher-Hartwig singularity. So even F is smooth, you still have Fisher-Hartwig singularities on the end. So my previous formula immediately can give the answers for this thing, and as a result, we prove several Forrester-Frankel conjectures when they derived formulas for this thing. Some of those under some restrictions, some of those surplus terms also were proven by Bazor and Eilhart, but not all. Thank you very much. So this is.
So a remark that I'm not sure if it was quite from the perspective of orthogonal polynomials, but Forrester and Whitty have a paper. Forrester and Whitty have a paper where they talk about random matrix type solutions, function for P6, and they do get in particular sort of start from the general solution of the hypergeometric equation, so they do get this sort of jump popping up, and so at least in the P6 case, so I guess if you have just -1, 1, and one other singularity in between, in that case, by their results is P6.
No, of course. Well, my last results, they more or less has nothing to do with orthogonal polynomials. So this is, so it is just for as I said, for Fisher-Hartwig. But it is orthogonal polynomials on the interval.
Yeah.
On the interval with the Fisher-Hartwig weight. Eric, I don't quite get what you want to say.
I'm just saying that it's sort of the minimal interesting case where you have a singularity between 0, -1, 1, but exactly 1. That by their results, this Hankel determinant is essentially a tau function for P6. It's sort of the general hypergeometric tau function.
Yeah. Okay. So. Okay.
It was a remark, not a question.
Okay.
Any other questions or remarks? Okay, in view of the time, probably I think leave the. Thank you.